Okay, we'll see what we can do.
Okay, we're going to go ahead. Next up, we have a series of short presentations about resource providers. Next up will be Nick Nystrom from the Pittsburgh Supercomputing Center. Nick, take it away.
Hey, thanks, Scott. So, as Scott said, I'm Nick Nystrom. I'm Chief Scientist here at PSC. I'm going to give a whirlwind tour of the Exceed resources we have here at Pittsburgh. This is more material than I can cover in today's talk. But the slides are there for those who want to go back. Please ask me questions offline if you need them. So very quickly, there we go. We're going to present really three things. Bridges, which is available now, also Bridges AI, also available, and Bridges 2, which we're going to build next summer. So Bridges itself,
Nick, can I interrupt you? Your audio is a little soft.
And John Urbanic, who I assume you met through this institute. The one slide for Bridges is here. It is a fairly large system by NSF standards. It's been running since 2016. It features a large number of Xeon cores, also GPUs, with the Bridges AI expansion, which we introduced this January. We also introduced a number of voltage GPUs. The point of Bridges was really to bring in people who've never used HPC before, make HPC as usable as a laptop. And we did that through several means. It is the heterogeneity of the hardware, giving people CPUs, GPUs, and very large memory. And then on top of that, putting a very flexible software environment, featuring things people use everywhere, like Python, Anaconda, Jupyter, R, MATLAB, letting them access those on extremely large memory nodes, up to 12 terabytes of RAM. And putting all this together lets people do things that are 2 or 3 orders of magnitude bigger than they can do on their local resources. Excuse me. Been successful. To date, we've served over 16,000 users, over 2,100 projects, and these people have been at over 800 institutions in the US, plus collaborators worldwide. And what I think is really interesting about the machine, we were supposed to serve new fields of science. And the last time I looked, we were spanning 122 NSF fields of study. And that's a bigger number that I've seen for other systems. It really is a majority of the fields of study in the NSF rubric. And so it says that this system is doing what it's supposed to. This was the first deployment in the world of the Intel OmniPath fabric that we actually had a hand in designing quite a long time ago now. It's designed to make advanced computing easy. And the way it does that, like I said, it's in the green box. These are ways it differs from what we think of as a traditional supercomputer. And so the first is we really prioritize interactivity. There's an easy command called interact. Actually wrap around the Swarm command, but it's designed for ease of use. That will get you on the node goals immediately, regardless of what node type you're after. We scale the boundary of how many nodes are allocated to interactive work versus batch to accommodate what we anticipate need for interactive to be. We support all the popular languages I mentioned, AI frameworks, and those are right now primarily through containers. We maintain the local Singularity repo of containers from NVIDIA's NGC Cloud Docker repository for ease of use. We support databases, persistently, virtual machines, and those really drive what we call science gateways, or persistent web services. They're typically around individual domains. We support community data sets. We have a large collection of applications and libraries. And all together, it makes a very productive programming environment and a really environment for analytics. So a cartoon of the system is here. It's actually an old version. I update this one. There's a live link at the bottom, psc.edu/pbt, for the Bridges virtual tour. And that version is live. You can click on it. You can see what each node is, what the CPUs are, what they're good for, and also workflows of how the whole system is designed to do many different things at once, how it separately serves HPC jobs, AI jobs, large memory, heterogeneous workflows, and so on. Hadoop, Spark, and all these different things. The blue bubbles here represent the ways that the system is designed to do machine learning, AI, and data analytics. And really all the components factor into that. This is important because as we move forward, Bridges 2, we carry these concepts forward because they work. At the bottom right here is Bridges AI. And the new version of the virtual tour is integrated in. And we'll talk about that in a moment. Community data sets are a big part of this. The way we think of community data sets, we're having these data repositories a large number of people can use and do science from, and especially where they could do correlations and cross correlations between them, is really a way of democratizing science. Just as a large telescope or particle collider provides the input for a large number of physicists or astronomers, data sets provide fodder for people to do analytics, to answer research questions they've never asked before. So we host these. These are just some examples. These are mainly around sentiment analysis, images, web scale crawls, but we also have things like the Cancer Genome Atlas, other large bioinformatic databases, genomic databases, and things that let people contribute to science no matter where they are, whether it's a tier 1 research school or a rural, even a community college, or we even have high schoolers contributing. That's created a whole ecosystem around Bridges where we have many large projects that have grown around it. We started with the top right, this one called Big Data for Better Health. And the point of that was to bring together machine learning and big data for the life sciences. That was a collaboration between Carnegie Mellon and Pitt. In that case, they decided they needed another 2.5 petabytes of storage persistently, not to have to write annual exceed allocations because they weren't sure they'd be renewed every year. And really, 2.5 petabytes is a fair amount. They didn't think they'd get that. So we worked with them. We purchased the storage on their behalf, leveraging our processing power just to get good pricing. And we connected the Bridges by OmniPath. That's been serving a number of projects. It's been serving one around cancer, for breast and lung, others for causal discovery, still others, a new one in breast cancer funded by the Aurora Foundation. And so that was really a pilot. That showed that we can build other big data projects around this architecture that we designed to be extensible. That then led to the Brain Image Library on the lower left, for Bill. The Brain Image Library is about 10 petabytes of confocal fluorescence microscopy data. And again, in that case, they bought the storage, but we're leveraging the Bridges for the compute. It's a great economy of scale, a great way to bring resources together and to do things that could never have been done otherwise. That then led to the top left, which is a Human Biomolecular Atlas program. And I'm PI of the infrastructure and engagement component of that, which is really central to the whole program. We're still going to find out how big the data for that will be. We're going to have our first public data release next January. This is accepting data from 5 tissue mapping centers around the country: Stanford, Caltech, San Diego, Vanderbilt, and Florida. To really build a single cell atlas of the human body, all major tissue types, genomic imaging, and mass spec data. So we understand everything from genomics, histology, and protein expression for all tissues in the body. And that is now a collaboration too. We're also working with the Human Cell Atlas, the Human Tumor Atlas Network, and all of the other major collaborations around the world to bring these big data sets together and make them interoperable. And so that's what Bridges has grown into. And by building this very extensible architecture where we encourage things like containers, analytics, machine learning, and data, it has continued to grow. The next slide is just what's available on Exceed. You can get this from the Exceed pages. Main point here, though, is that for startup allocations, we can turn those around usually on a business day. They're substantial, especially for the GPU ones. And then for the research allocations, they're quarterly. Those are about 2 orders of magnitude bigger. And again, quite substantial. We can also make this available for private sector on cost recovery basis. Get you more information on that for anyone who needs it. The next application deadline is probably coming up in 2 months, the January round. So Bridges AI we introduced, we brought the hardware in last fall. The real leaders behind this are myself and Paula, who is our director of AI at PSC. It introduces an NVIDIA DGX2, which is really the most scalable resource in the world for deep learning training. 9, also powerful, but not quite as powerful, Hewlett-Packard Enterprise Apollo servers. We'll go into details on each of these. This is all built into Bridges. It's fully integrated with the file systems, with other processors. So this can all be used together. And it introduces a tremendous amount of performance through the new Volta GPUs, and the Tensor cores are part of those. We also have funding in this supplement for staffing to help people scale their models up to this tremendous resource, because frankly, most models are designed for consumer GPUs on a laptop or desktop. And so the heart of Bridges AI is NVIDIA Volta. As you probably know, it contains tensor cores. Tensor cores accelerate the little matrix operations that are needed for deep learning training, especially. It also includes HBM2 high bandwidth memory. What's really great about this is the bandwidth per chip is 900 gigabytes per second of the HBM2. You compare that to state-of-the-art Xeons, they're more like 25 to 50 gigabytes a second, which is good, but this is 30 times bigger. And that lets you do the training a lot faster. So between that and the tensor cores, that really is game-changing. We put in 9 of these Apollo 6500 servers, recognizing that not everyone needs the very biggest system possible for training, and there's a premium price for that very big system possible. But if you have 8 Volta GPUs in a box connected by NVLink 2, you can do amazing things. NVLink 2 is 300 gigabytes per second. Just amazing bandwidth. I'm not going to do a lot of detail here. These all have SSDs in them for storing data sets to do the training on locally. They're connected by OmniPath to the overall system. And so one can benefit from data sets on our Lustre file system, bring them in here, stage them into SSDs or a memory file system, and do just amazing things with deep learning. Also in Bridges AI, we put in one NVIDIA DGX2. The point of the DGX2 is the very maximum possible training performance, 16 volts, 512 gigabytes of HBM2 memory, 30 terabytes of in-system SSDs, and an NV switch that couples all these at full bisection bandwidth of 2.4 terabytes a second. And so for anyone needing to do training of whatever, RNNs, CNNs, GANs, anything like that, this is the place to be. I'd encourage anyone out there who's doing AI to just apply, get a startup and get going. Be happy to have you. We support all the major frameworks, typically through the NGC NVIDIA GPU Cloud containers. And what those get us is always the most current version of the framework and also fully optimized for these systems. It gets around the problems of having to build things, make sure they're built ideally. Bridges 2, we were awarded on June 28th. This is a similar cast of characters at PSC driving it. It's myself for overall leadership and the operations, Paula for AI and data, Sergio Stanilevich, who most of you know for user support, and Robin Seebeck is now leading Broadening Impact. This was designed to address rapidly evolving science. What's that mean? Rapidly evolving covers a number of things. It still embraces high performance and high throughput computing. Those continue to be very important for simulation modeling. It also includes high performance AI, or HPAI, and then coupling AI with simulation through use of surrogate models and online inferencing. Community data continues to be vitally important because data sets drive a lot of the science now. We continue to emphasize ease of use, familiar software stacks, productivity. And putting that all together with data-intensive workflows, means for maintaining provenance, managing very complex data sets, collaborations, access controls, data use agreements, so on, and coupling to cloud. So Bridges, as we said, introduced a number of things. Very successful in terms of number of users, 130 education allocations. Bridges 2 carries those concepts forward. I haven't done the virtual tour for this yet. I'm just getting time to do now. The main keys here are several. One is rapidly evolving, speaks for itself. Artificial intelligence is a huge part of that, both for data analytics and for accelerating simulation. And we're introducing Intel Ice Lake CPUs. Those got several things. One, as Intel's first 10 nanometer processor, they're amazingly power efficient. That means that Bridges 2 will actually draw less power than Bridges 1, even though it's much faster and more powerful as a computer. It consumes less watts. That's good for us. It lets us put money into people to help with science, and it's better for the planet. Moreover, Ice Lake also moves to PCIe Gen 4, which lets us go up to full HDR 200 InfiniBand for improving the bandwidth between nodes. We need that because the nodes here are much more powerful than nodes in Bridges by about a factor of 3.2. And the third thing is that Intel Ice Lake has vector neural network instructions. These are new instructions in the Intel architecture to accelerate deep learning inferencing. And it turns all Bridges 2 into really a large, coherent AI engine, excellent in both training and inferencing. So full system high performance AI, Ice Lake, we're introducing a flash array. Will accelerate training, genomics, and other applications. A new tiered data management system, recognizing that for really big data, maintaining a second copy at users' home institutions just as impossible. They don't have that storage. So we can do that here. And cloud interoperability. As a very quick overview of why this is important, I just wanted to trace through. This is a story that Paula had developed on the evolution of AI and what we've been able to make possible here at PSC by looking at these new architectures we've designed to make it work. Back in 2010, D'Artagnan ran on Blacklight. This was a very large shared memory machine we had here. It won the World Computer Poker Championships by using large shared memory. That then evolved into a new program called Claudico, which was the first to defeat the top human players in Texas No Limit Hold'em poker. That was demonstrated against humans in 2017. Very nice science paper. It generated the Best Paper Award at the NIPS Neural Information Processing Conference. And that was great. In 2017, everyone said, this is great. It beat the world's top professional players. But will it ever be able to compete in six player? And people said, no, that's way out there. We haven't seen that coming. Well, now it's 2 years later in 2019, and that's been done. So now the next system out, Pluribus, has done the same thing against the world's top pros in 6-player. This is important because, moving to the next slide, this was awarded the Marvin Minsky Medal for Outstanding Achievements in AI. And the quote from Michael Woolridge, who is the chair of this awards committee, points out that poker is just a placeholder for situations where you don't have complete information and where you have adversaries who are actively changing their strategy against you, such as everything in the real world, like economics, strategic negotiating, cybersecurity, stem cells in the human body, and so on. There have been 2 companies formed out of this. It has real-world applications in medicine, security, and defense. And it's a demonstration of how NSF investments in infrastructure are leading to things of real national importance, and how emphasizing AI, which by a while ago was just a demonstration toy problem, is now of very real importance. And we have many of these from the scientific domain as well that I don't have time for. Bridges 2, I'm going to go through this quickly. The diagram that's analogous to one in Bridges 1 is like this. The boxes outlined in dark green are brand new elements. So those in Bridges 2 are the flash array and the tape archive in the center and left. Everything in the light green outlines, which are all compute nodes, bottom, are bigger, better, faster than Bridges 1. New versions of things, new CPUs, new memory, higher bandwidth, just everything better. And then other things like the service nodes are just, they're also faster because everything has become better. We've shifted to Mellanox HDR InfiniBand interconnect, and that lets us connect to GPU nodes through GPU Direct over remote direct memory access or RDMA. And it means we get to connect these 24 8-way servers also at very high speed to do scalable AI and couple that with simulation as needed. But overall, it makes a very strong machine. Like Bridges, we designed this fully out of edge or spine switches. And that really is the cost-effective way to build a system of this size, especially for data-intensive problems. The data infrastructure is that we have 3 tiers. We have a flash array with 160 terabytes of flash that gives us really high performance of 9 million IOPS. They're great for deep learning training, graph analytics, genomics, various other applications. On the right in the blue box, we have disk and tape. The unified namespace managed by HPE's DMF or Data Management Framework. Many people who have been around for a while know that as the DMF has a long history in HPC. It's very mature, very stable, very reliable. The disk is RAID Z2, so that's very high reliable. Reasonably high performance, 15 petabytes usable. That will be allocated through Exceed as the storage allocation. The tape is here for data sets that are truly precious. So for HubMap, for example, we have input from tissue mapping centers, large-scale sequencing, imaging, genomics, and so on. That's not reproducible. We can't get those humans back to do the analysis again, and we could be time prohibitive. We have to have spare copies of that. They're safe from not only hardware problems, but also possible software faults and human error. That's what the tape is for. And this is designed to be fully scalable in all of these levels so that if, for example, a project came along and needed an additional 10 or 100 petabytes of tape for archiving, through their own project funding, we can very economically add that. The ideas of productivity, usability, and interoperability continue to be very important. This is looking at the multimodal data and community data sets serving non-traditional users, offering big data as a service, all integrated with DMF, as I mentioned. Usability comes to all of the programming models we mentioned, frameworks, the languages, everything that people are using anywhere else we want to be able to service here as well. And as transparent as possible. Interoperability is everything from campuses, clouds, to individual large projects and instruments. We're working now with Fermilab on things with the Large Hadron Collider, with other cloud projects. HubMap includes a cloud element with AWS and GCP. Campus clusters, we co-locate those. We offer co-location for those who would like to have equipment next to our big machines to leverage both large storage and burst computing. Along with that is the criticality of user support. We maintain a very high emphasis on this. PSC always has. We run the Exceed Novel and Innovative Projects program. I would say for people that have interesting projects, especially machine learning and data, contact us. We have additional resources we can bring to bear to help scale things up, get them going, and really push the science forward. We'll have an early operations phase for Bridges 2 starting October 1, very soon. Now let's speak more about that in just a moment. There's a very extensive broadening impact aspect to this. Everything in the NSF broader impact portfolio, STEM talent, look to the future, impacts on society, going beyond borders. and engaging everyone. If you have other people who'd like to participate, if there are schools that would like to have engage with us on curriculum development, on training programs, internships, we welcome all of that. Application areas, so the point is, we build systems to solve science, get things done, not just to employ cool hardware. There's a lot of that. Some very quick examples I'm almost done here of how we'll move this forward. Gene expression. This is an example of people bringing together deep learning and genomics to understand how genes are being expressed in various tissues. Second on the top is digital pathology with Joel Saltz at Stony Brook. We have a paper we're presenting at the Carla Latin American HPC conference next month, featuring this work. UpMap we've talked about. That's really very big data. We don't know how big now. We're estimating 10 to 100 petabytes. Using bridges and cloud interoperably for analysis and collaboration. Smart cities look at Internet of Things and sensor data. In this image, look at movement of pedestrians, bicycles, traffic, and objects through an area in the center of Pittsburgh, and automatically recognizing what's happening, be able to do urban planning. Okay. Yep. So I will move forward. I'll not go through the other four. They're fairly self-evident. Target timeline for Bridges 2 is, as I said, October 1st is the start of the award. We will begin accepting extract proposals for this machine during next June to July. And October 1, we start productions. We'll have an early user program next August. For people who would like to engage with it, please let us know. We'd love to have you. And until then, Bridges 1 is a great place to get started. Quick summary, I'll just leave here for you to read. These are three systems that exceed right now: Bridges, Bridges AI, and Bridges 2. Really, the first two are part Bridges. They're available now. Come get them. Bridges 2 will be next summer. Early user program. Would be happy to have everyone that would be interested. So thanks for your attention. Please, I don't know if we have time for questions or not. If not, send them by email. If we do, I'll stick around.
Thank you very much, Nick. We'll let people go ahead and post questions online for you to answer, and we'll